Good morning. Today, we move in the direction that takes a big turn from the direction we've been going in so far. All the devices we had up to now, resistors and voltage sources and even your digital devices like the AND gate or the inverter and so on, had a very specific property. Okay, we didn't dwell on that property, but that property was that these were not what are called memory devices. In other words, the outputs at any given time are a function of the inputs alone. Okay, in other words, if you took your inverter or your NAND gate for that matter, and you built a circuit comprising 15 AND gates connected in structures that we've talked about, you apply an input and boom, you get an output. And your output is a function of the inputs alone, right? Same way with your resistors and voltage sources. At any given point in time, your output, VO of t, was some function of the input, VI of t. What we're going to do today is discuss a new element, okay, which will introduce a whole new class of fun stuff for all of us to deal with. Okay, and that's called storage. In other words, the output of a circuit is now going to depend not just on the inputs, but it's going to depend on the background, or it's going to depend on where the circuit has been in the past. Okay, so past is going to matter. Okay, it's a very fundamental difference. And what I'd like to do is start by, giving you folks a little bit of a surprise. So I'm going to do a little demo, taking two of your inverter circuits. So I'm going to start by taking a couple of inverters. Okay, remember I'm using this structure here as an inverter. And I'm going to couple this to another inverter and take an output C, some Vs, some load resistance RL, my B terminal and my A terminal. So I'm going to apply some input between ground and my A terminal. And for fun, I'm going to apply a square wave at the input, a square wave between 0 and 5 volts. And this is how my time goes. Let's assume that Vs is 5 volts. So what I'm going to do is plot for you the behavior of this inverter. Okay? I'm going to plot for you A, which should look like this. I'm going to plot for you B, which should be an inverted waveform. And then plot C, which should be a waveform that looks like this again. All right, so let me do a plot here. So this is A. And so on. Time goes this way. And let's say this is between 0 and 5 volts. And B should be an inverted waveform that should look like this. If all that we believe of the world so far is true, then this is how things should behave. So C should look like this, right? Okay, so this is what the world should look like, and if everything that you've learned about is true and correct and all of the good stuff. So let me show you a little demo and see if I can try to pull the rug out from under all that you've learned so far. Okay, and show you some sort of some surprising stuff. So, so up here, so here are the three waveforms that I show you up here. So this is my A. This is my A waveform. This is the B waveform. Notice that B, as you expect, is an inverted form of A, and this is C. Okay, we all expect this, correct? But what I'm going to do is let me expand the time scale on this so that I can look at these transitions a little bit more carefully. Okay, I'm just going to expand the time scale. There you go. All I've done is expand the time scale and spread that out a little bit. Okay? And what you see there is quite different from what you expect. Okay? A is, is a square wave as expected. But B is stunningly different. Okay? It's a 0 as expected because this is a 1. But here I get some really strange behavior. Okay? A behavior that is like nothing on earth. Okay? Like nothing we've seen before. And then, of course, it becomes a 1 eventually, but there's some really, really shady stuff going on here. Okay? And so far, you're not prepared to deal with this. Okay? We haven't given you the facility to deal with this issue. What's the problem with this? Now, we could say, who cares? What's the problem with this? Let's look at the result. So I'm looking at this. I'm focusing on this piece here, and notice that instead of being a sharp rise, it looks like this. Okay? It's going up a little bit more slowly. What kind of problem would that create? The problem that creates is the following. Okay, let me play around with this graph a little bit more. What I'm going to do is just take this output here, the C output, and line it up against the A output. Okay? And so I'm going to line up the C waveform on top of the A waveform so you can see for yourself if something really, really strange and nasty is happening. Okay, I'm just going to move up the C waveform and line it up. What's happening out there? If you look carefully, what you observe is that the C waveform transitions just ever so slightly later than the A waveform. Okay? Look here. And I claim that it's because of this. Because of this, the C waveform falls just a little bit later. Okay, and that little thing we see out there is a delay. Okay, so nothing you've learned so far prepares you for this. Suddenly, instead of the output exactly following the input, my output is following the input, but a little bit later. Okay? And it is this fact here, it's this fact of life, that things happen a little bit later, is really the reason why each of you and all of us keeps buying new computers every couple of years. This simple, basic fact. If this fact of life didn't exist, you would buy one computer and be done with it for life. Okay, Intel would make a gobs of money 1 year, and so would Dell and Gateway and so on, and then no more. That's it. This is it. But because there's little itty-bitty difference here, okay, our entire semiconductor technology is charging along, trying to do something about that. You buy newer and newer computers each year. It turns out this little itty-bitty thing here, that is called the delay, the inverted delay. Okay? And it happens because of a specific element that has been introduced here that we haven't shown you so far. And a large part of our semiconductor industry and follow-on courses and design and so on focuses on how can I make my delay smaller? How can I get to be faster and faster and faster? Okay, this relates to how fast we can clock your Pentium 4. Okay, remember it went from, it came out at 1.3 gigahertz? What's the fastest Pentium money can buy today? What's the fastest P4? Oh, 3.2s have come out? I don't know. Ken claims 3.2. But yeah, there you go, 3.2 gigahertz. It's all got to do with this little itty-bitty thing. Okay? You saw it for the first time here. Okay, when some of you go become, CTOs at Intel and so on, just remember that it all began on October 16th, with this little rinky-dink thing here. Okay, so what you're going to learn now is some really cool stuff, okay, that has huge implications for life. So why does that happen? So why did this transition happen just a little bit later? Okay, the reason is that, remember, when this waveform reaches VT, the threshold voltage of this MOSFET, this guy is going to switch, right? So because of the slower rise of the voltage, the VT is going to be reached ever so slight, a small amount of time later. Okay, so I'm going to hit VT slightly later, and because of that, this guy is going to transition just a bit later. Okay, because this intermediate waveform B is slower, it hits VT just a little bit later than if it would have made an instantaneous transition, and therefore my output falls just a little bit later, and this gives rise to my delay in the inverter. Okay, we can call that D if you like. Okay, some delay. Okay, so in your course notes, this material is covered in chapters 9 and 10. So that was to kind of motivate why we're going to be doing all that we're doing for the next. Don't anybody come within a foot of this even by mistake. It's and I mean it. It's pretty deadly stuff. Okay. So so today we talk about the capacitor. Okay, and in the next couple of lectures, I'm going to tie it all together and show you how this relates to that. Okay, shows you exactly how the delay happens. You can compute it based on some simple principles that you learn about in the next couple of lectures. Okay, so what I'm going to do is, first of all, show you, I claim that that delay happens because of the presence of a capacitor somewhere in there. Okay, what I'll do now is take you into a closer look, at the MOSFET and show you where the capacitor is. So this is the MOSFET that you've seen so far, drain, gate, and source. Okay, this is called an N-channel MOSFET. And what I'm going to do is dissect this and show you what's actually happening, what this looks like on silicon. Okay, so the MOSFET is, so here's my slab of silicon. Okay, it's very thin. And let's say this is, I won't go into details here. You'll learn a lot more about this in future device classes like 301 and so on. But suffice it to say, I'll just introduce it here to give you a sense of where the capacitor is. So this is P-type silicon. And the way you build a MOSFET is you create a couple of tubs in which you dope to be N-type. Okay, the basic silicon here is doped P-type. And this guy here is N-type. And what you do is a thin oxide layer is placed on top of that. And then, on top of that, a thin metal layer. Okay, this is a metal layer. This is a thin piece of oxide, silicon dioxide. Okay, and this is my P substrate. Now, this is a little metal layer that's really a wire on top of the silicon. Okay, this metal layer, could be some sort of a wire that meanders around on the surface of silicon, and this is the wire that connects to the gate. This is the gate of my MOSFET, and this guy here is the drain, and this guy here is the source, and this is my gate. Okay, so there's a little piece of metal here. This is this piece of metal here. And there's a piece of oxide, and then my silicon substrate. So notice that this is my oxide. When I apply a positive voltage to the gate here with respect to the substrate, what happens is that I draw up negative charges up, draw up electrons up here into this channel region, and I have corresponding plus type out here, so that I get a view here that looks like a couple of plates. Okay, it's a couple of plates, and I end up with an oxide in the middle. There's no connection. Okay, 2 plates separated by a small distance. Okay, with plus Q and minus Q on the plates. And because of that, what ends up happening here is that this piece behaves like a capacitor. Okay, so you have a capacitor has 2 plates with a thin insulating material in the middle, and with some dielectric, with some permittivity epsilon, and so I get a little piece of a capacitor here. Okay, that's the capacitor that is formed. Okay, I didn't set out to build that capacitor, but there is that capacitor nonetheless. So when I apply a positive voltage at the gate, negative electrons are pulled up here, which forms a channel, and then current can then flow, and that's how the MOSFET turns on. Okay, so N-type electrons back to N-type, and I get electron flow here, and that gives me my channel. This is just kind of, devices in 4 minutes or less. You will do an entire course on this if you like, if you take 301. So what we do is, to be able to capture the behavior that we just saw, the funny delay behavior, we have to augment our model. We have to introduce a new element. Okay, so what we do is, here's a MOSFET, gate, drain, and source. And notice here, we model this by putting a little capacitor, CGS, between our gate and the source. Okay, so this becomes a simple model for our MOSFET device, which is the good old gate, drain, source device from the past, with a little capacitor, CGS, having some value for CGS in, maybe 10 to the minus 14 or thereabouts farads. So that's a little capacitor that has come about in this device that we fabricated here. So it's that capacitor that is at the node B, between the node B and ground, because it's between the gate and the source of the second inverter. Okay, and it's that capacitor that's playing the games that we saw out there. So let's look at some of the behavior of an ideal linear capacitor. So a capacitor, as I said, has a couple of plates. There are a couple of plates. Between the plates is some dielectric, permittivity epsilon. Let's say the area of the plates is A, and let's say the plates are separated by a distance D. Okay, I get some charge here, let's say Q, so Q and minus Q on the capacitor. And the capacitance C is given by epsilon A divided by D. Okay, where epsilon, as I said, is the permittivity of the dielectric. Okay, so if it's free space, then it would be epsilon 0, which is the permittivity of free space. So that's the capacitance in farads. And the symbol looks like this. Capacitor C, voltage V, current I. So this, much like the resistor, voltage source, and so on, this now becomes a primitive element in your tool chest of elements, okay, like the voltage source and so on. Capacitance with the voltage V across it and a current I, and I've assigned the associated variables here according to the associated variable discipline. A question to ask ourselves is, remember we said we're all now in a playground from all of nature in this playground where the lumped matter discipline holds. Okay, and also remember that we said that for the lumped matter discipline to hold, we have to make a couple of assumptions. One of those assumptions was that dq by dt for all our elements should be 0 for all time. Okay, so right now, what about the capacitor? Okay, it's got some charge, Q. Okay, so charge must have built up somehow. Okay, so does that mean that I lied all along, that we're no longer in this playground, that we've been ejected from the playground because of the capacitor? Or are we still in the circuits playground in which the lumped matter discipline holds, and all good things happen, and so on. That seems like a contradiction, doesn't it? I said, I took you from Maxwell's playgrounds to the ECS playground, where I said the lumped matter discipline holds. And one of the foundations of the LMD was that dq by dt should be 0 for all time inside the elements that we're going to deal with. And right now, boom, it's not 4 weeks into the course, and Agarwal introduces an element, and it's got Q in it. Okay, it turns out that the capacitor also adheres to the lumped matter discipline. Remember, the discipline says that dq by dt is 0 for all time within elements. Okay, so I'm going to be clever. What I'm going to do is I'm going to choose element boundaries in a very clever way. Notice that if I have Q here, okay, on this plate, then I get minus Q on the other plate. Okay, so if I take the whole element, the element as a whole, okay, if I'm careful in terms of how I package my boundaries, okay, if I put both my plates inside my boundary, my element boundary, then I still do get the net charge being 0. Okay, so dq by dt is indeed 0 for all time, provided I make sure that my element has both the plates. Okay, so therefore, if you come across somebody else that gives you an element that says, I have an idea, let's create a new branch of electrical engineering in which we model a capacitor not as one element with 2 plates, but let's build a capacitor, by combining 2 new elements. Okay, some 2 garbage elements called G1 and G2. The G1 is like the top plate, G2 is the bottom plate. I put them together, I get a capacitor. But notice, if I just pick one plate, then the element G1 will not adhere to the LMD. Okay, it adheres to the LMD because I choose my element boundaries in a way that both plates come within it. Okay, so it's very fundamental and key, and you can read a lot more about it in the course notes. Okay, so I purposefully dwelt on that simple point because I think it's foundational and important, and you really need to understand that the capacitor does satisfy LMD. We are still in the good old playground. Okay. So a few simple facts here. These are in the notes, and you've also seen this before, I'm sure. I can relate the charge to the capacitance and the voltage as Q is equal to CV. And Q is in coulombs. This is in farads. And this is in volts. Okay? So there is some charge Q stored on the capacitor. And it's in coulombs, and Q is equal to CV. So I can differentiate this with respect to time to get the current. And that becomes I is dq by dt. So the current at any given time is dq by dt. And so I substitute for Q in terms of CV here. That's what I get. Okay, so the current I is d by dt of CV. A 6002 assumption. Okay, and capacitance in general can be time varying. Okay, I can get time varying capacitors. In fact, there are some sensors which are capacitive, and as I talk, my sound waves can change the pressure on the top plate of the capacitor and move the top plate of the capacitor, thereby changing the capacitance by moving the plate. Remember, D here, as the plate moves closer, I get a higher capacitance. So we won't be dealing, unless explicitly said so, with time varying capacitances. Okay, so what we can do is a 6002 assumption allows us to write C dV dt. Okay, so my current to the capacitor is C dV dt. I can also write down the energy. Capacitors store energy, and energy is given by half CV squared. Okay, I'm sure you've seen all this before in physics and so on. So that's the amount of energy stored in the capacitor if it is holding a charge Q. So let me do a little demonstration for you. So our friend Lorenzo, they don't make glasses like they used to. So our friend Lorenzo has charged up this capacitor. Okay, it's a huge capacitor, and it's a 250-volt capacitor. Okay, so it's nasty. So he's charged it up, and he's kept it there. And to show you that it does contain stored charge, it's been sitting there holding charge, right? Maybe the first row should kind of just go backwards. Just step back for a second. I think you guys would be safe, but you know, I just don't want to take any chances. So this is holding a bunch of charge. It's kind of sitting there. So if I short the terminals, it should, you know, it should try to say, oh, I got a path. Let me get my charge out. So all right, let's do it. This is always a scary moment for me, and I say a little prayer before I do this. Good? Okay. Gee, you guys would love to see me getting fried, huh? All right, let's see. So it did contain charge. Shall I just make sure? Okay. So there's a reason why Lorenzo puts one hand inside his pocket when he shorts it. Because there's a natural tendency to hold the wire with both hands and say la 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 and go and put it across the capacitor. So by doing this, you're guaranteed that you'll just be using one, touching it with one hand. Okay. So I think hopefully you folks will remember for life that a capacitor can sit around and hold its charge for a while. Okay. All right. That's enough for fun and games. So let's get on with the business of building circuits. So what I'm going to do is, as I promised you, I'm going to close the loop on that example by halfway through the next lecture. Okay, so I'm going to take you on a bit of a journey involving capacitors and resistors and involving some analysis, and then we'll close it all up for you in about the middle of next lecture. So what I'd like to do next is, here's a new element. Okay, and let's do some fun stuff with the elements. Well, you know about voltage sources, you know about resistors. Let's put them together and see, how they behave. Okay, so let's have a capacitor here, C, Vc of t, and some current I. Okay, what I'm going to do, in general, whenever I have something new or something strange, let's say like a capacitor or some other device, it's interesting to model the rest of the circuit behind it if it contains only resistors and voltages and linear elements as a Thevenin equivalent. So let me do that. Okay, this is R. And this is VI. Okay? So this stuff in the back is my standard pattern, voltage source in series with a resistor, and I connect that across my capacitor. By the way, remember, although you saw those funny waveforms and so on, the capacitor is a linear device. Okay, because you can see from here that the current relates to dV by dt. Okay, that's a linear operation. Okay, you don't see V squareds and VIs and things like that in there. So it's a linear device. Okay, so let's take a look. So let's go back to our trusty old method, the node method. Okay, if you just blindly apply the node method and simply grunge through a bunch of math, you should be able to get to the answer. That is, for some voltage V or some form of voltage VI, I should be able to figure out what VC looks like. So let's do that. So this is the node that's of interest here with the unknown node voltage VC. So let me apply the node method. So VC minus VI divided by R is the current going this way. That plus the current through the capacitor should equal 0. Okay? And what's the current through the capacitor? The node method tells me that get the current in terms of the element values, right? So we know that the current is given by C dV dt, C dVC dt equals 0. All right? So just shuffling things around a little bit, I can write RC dVC dt plus VC equals VI. So by writing the node equation, I then get the equation that characterizes this little circuit. Notice here that this has units of volts, okay? And since I have time here, this also must have units of time. Okay, so let's go about solving this little circuit and understanding how it behaves. The specific example that we will look at looks like this. Let's say the capacitor voltage at time t equals 0 is V0. This is given. Okay? So at time t equal to 0, I'm telling you that the capacitor contains a charge, and because of that, there's a voltage V0 across it. That capacitor had a voltage of 250 volts across it. In most of the devices we deal with in laptops and so on today, like the Pentium 4, voltages are on the order of 1.5 volts, very, very small voltages. All right? And so that's the value on the capacitor, the voltage. That's called the state. This is called the state. Capacitor state. It's the state of the capacitor. And I also give you that VI of t is VI. Okay? So my voltage is VI. And somehow, I'm not telling you how, but somehow I've arranged to have the capacitor voltage be V0 at time t equals 0. Okay, now I'm going to look for the solution to this for times t greater than or equal to 0. And in that time, my voltage VI is at some capital VI, some DC voltage VI. Okay? So I'm going to solve the differential equation RC dVC by dt plus VC equals VI. Okay, given these two values. Input is DC voltage VI, and VC0 is V0, the initial charge in the capacitor. So to solve this, so from now on till the almost till the end of the lecture, it's just going to be math about solving this very simple first-order differential equation. And the key here will be that throughout 6002, we will be following one method to solve these. There are many methods of solving differential equations, and we will follow one method. That method is called the method of homogeneous and particular solutions. Okay, in 1802, I believe, you would have learned about maybe this and certainly other methods. Okay, you can use any method to solve it. We'll just stick to one method, and this is also used in the course notes. So in this method, what we do, we take the solution VC by finding two other components. One is called the homogeneous solution, and summing that up with the particular solution. And that's the total solution. The total solution is sum of the homogeneous and the particular solutions. And the method has 3 steps. Okay, as I said before, we will be using this method again and again with every differential equation that we encounter in this course. And you won't encounter a whole lot. So the first step, we find the particular solution. Okay, the second step, find the homogeneous solution. Okay, the total solution is the sum of the two. Okay, and then find there'll be some unknown constants, and depending on the equation that you have. And in the end, we simply find the unknown constants by applying the initial conditions that we have. Okay, boom, boom, boom. Particular, homogeneous, find constants. Particular, homogeneous, find constants. Three things. So let's go about solving this equation and apply those three conditions. Again, remember, what I'm doing now for the next 10 minutes or 15 minutes, okay, is using math that you know about to simply solve this first-order differential equations. Okay, there's nothing really new that I'm going to talk about here. So one is to find the particular solution, VCP, okay, and which will then be added into the VCH to get me the solution. So where you find the VCP is you find any solution that satisfies this equation. Okay, this is the equation. You find any solution that satisfies it. Okay, and find the simplest possible solution that money can buy, and find it. That's a particular solution. Any solution is fine. So in this case, a really simple one would be VCP equals VI. Let's see if a constant works. Okay? One thing you will realize in differential equations is that they're actually much simpler than they seem. And the reason is that almost every time you have to assume you know the answer, okay, and then you're checking to see if what you assumed was correct. Okay, you assume the answer is this, okay, like you're really smart, and then check it out and say, oh yeah, that must have been the answer. So here, we assume that, I think VI is going to work, so let's try it out. So substituting in here, so RC, d by dt of VI is 0. VI is a constant. So I get VI equals VI, so therefore, this is a particular solution. Done. I substitute VI here. So dVI by dt is 0. So this vanishes. VI equals VI. Bingo. So therefore, VI is a solution to this equation. So I'm done with my VCP. And in general, what you have to do is use trial and error. Okay? By trial and error, try out a bunch of solutions. Okay, till you get lucky. In general, again, in all of 6002, for many of the excitations, a simple constant usually suffices. Our second step is to find the homogeneous solution. And we can also do that by very quickly. And to do that, we have to find a general solution to the homogeneous equation. The homogeneous equation is the same differential equation, but with the drive set to 0. Okay, we're going to follow a set pattern to solve the differential equations here. And the set pattern is find VCP, VCH, find constants. And to find VCH, we're also going to follow a set pattern to find the homogeneous solution. Okay? So we set the drive to 0. So VI is set to be 0. And I need to find a general solution to this. So as I promised earlier, diff equations are really, really simple because the way we're going to solve them is we're going to say, assume we know the answer, and then go check it. Okay? So let's try A e to the st. Let's try and see if this can solve this particular equation, okay, for some values of A and S. Okay, so I'm telling you, okay, that the solution is going to be of this form. Assume it. And then simply go ahead and find me A and S, and do that by substituting it back into the equation and find out the corresponding A's and S's. So let's go ahead and do that. So I get RC, I substitute this back up. So I get D of A e to the st dd plus A e to the st equals 0. Okay? And let me plug that in and see what comes. So I get RC, that A s e to the st plus a e to the st equals 0. Okay, I'm going to discard the trivial solution of a being 0. That's a trivial solution, so I'll discard that. And what I'll do is I'll cancel out the terms from, cancel out the a's from here, assuming a is not 0, and cancel out e to the st here. And what is left is RCS plus 1 equals 0. So what this is saying is that if I can find an if I can find an S, if I can find an S such that this is true, then a e to the st is a general solution to my homogeneous equation. Okay? And so S, this is easy enough, minus 1 by RC. So if I choose my S to be minus 1 by RC, then the simple math that I've gone through shows me that this must be the solution to the homogeneous equation. Or in other words, VCH is equal to a e to the minus t divided by RC. Okay, all this is saying is that a e to the minus t by RC is a solution to my homogeneous equation. A is an unknown constant. A is some constant. I don't know what that is yet. Okay? Notice RC has popped up again. And the cool thing about RC is that this is time. This also has units of time. Okay, so we commonly represent RC as some time constant tau, as units of time. So associated with that circuit is a time constant tau, which is simply RC. All right? So I commonly write this as a e to the minus t divided by tau. So I'm very near the end here. So I have the particular solution here. I've got the homogeneous solution there. Okay? Oh, I need to make one more, tell you about something else. And the way I found the homogeneous solution was in 4 steps. I assumed the solution of the form a e to the st. I assumed the solution of the form a to the e to the st. Okay? I created this equation here in S. Okay, this is called the characteristic equation for that circuit. Okay, we'll see this time and time again for RC and other forms of circuits. So assume a solution of this form, construct the characteristic equation, okay, find the roots of the characteristic equation. In this case, it's an equation in S, so this is the root. And then form the solution based on that root. Okay, 4 steps. A to the st, characteristic equation, root, and then write down the general homogeneous solution. 4 steps there. Okay? And finally, I want to write down the total solution. And the total solution is simply VCP plus VCH, and VCP was VI, and VCH was a e to the minus t by tau. Okay, tau is simply RC. That's my solution. Now, remember the last step. Last step was form the total solution and find out the remaining constants. And I'll find out the remaining constants by using my initial conditions. So I know at t equals 0, I know that Vc equals V naught. Okay, I know that. And so therefore, I can substitute t equals 0 to find the constant. So I know that Vc is V naught at t equals 0. So at t equals 0, this thing becomes 1. And so I get this equation, and from which I get A to be V naught minus Vi. All right, in other words, my solution Vc is simply Vi plus V naught minus Vi e to the minus t divided by tau. Okay, so the last 15 minutes have just been math. Okay, no electrical engineering here, but electrical engineering stopped at the point it wrote this differential equation down, went through a bunch of math, and came up with the solution. Okay, purely mathematically. Okay, so here I simply use math to get you the solution. And as I've been promising you throughout this course, in the next lecture, I will give you an intuitive EE method of doing it. Okay? Real electrical engineers, real EECS folks don't do it this way. Okay, real EECS folks do it intuitively. Okay, and I'll show you how to do it in four easy seconds in the next lecture. Okay, but you need to understand the foundations of how this comes about, and so this is the answer. All right. You can also get the current. IC is simply C dVC by dt. I won't do that for you, but you can simply differentiate it and get the current. So I can plot for you VC time t VC. The intuitive way of looking at this is I have VI, which is the final value of the voltage. Okay, when t is infinity, okay, this part goes to 0, so the output is simply, or the VC is simply VI. And then there's a component V0 minus VI, which decays according to this, starting out at an initial value of V0. Notice when t is 0, VC is V0. You can see that in the equation. And so it starts out at V0, ends up at VI. I start here, I end up here, and this portion, V0 minus VI, decays out over time, like this. Okay? And this decay is governed by the RC time constant, or tau. Okay? So I'm going to show you very quickly a couple of examples of waveforms, one that goes like this, and one that looks like this. This is when I start with some value V0, and I don't apply any input. It should decay down to 0. T, T, VC, VC. Okay, so if I apply 0 for VI, then this should simply decay down to nothing over time. And if I apply some VI, but there's no state on the capacitor, okay, then that same equation is going to look like this. Okay, you can go and confirm for yourselves that when I apply some input, but the capacitor has 0 state, I start at 0, I finish up at VI, and my waveform looks like this. So there you go. So that's the first one. The second one, where I have 5 volts on the capacitor. I'm sorry, where I have 5 volts on the capacitor and no input, and then I watch. So assume that at time t equals 0, I take away an input, short my voltage, the input voltage to ground, for example, apply 0 volts. You see the decay from 5 volts to 0 volts. And in the first case, I start with 0 volts on my capacitor. I apply an input of 5 volts, and notice that at t equals 0, and notice that the capacitor rises up to that level. So notice that these circuits with capacitors and resistors are typified by waveforms that are exponential rises and exponential decays. Okay, we'll see more of that next time.